so we'll pick up where we left off last class talking about probability. So I think something I had mentioned was getting another Learn Smart up there. Based off what we did Friday, I kind of changed my mind. So I cut the Learn Smart probably more than in half, and I posted it before my classes today. So it'll be due before we start class on Friday. It should, I've set the time, I set a targeted time. It was like 5 or 6 minutes. So it shouldn't take you long at all. But I do want you to try to get on, especially, probably the best would be if you could get on before Wednesday's class, but it's not due until the start of Friday's class to kind of give you a look at some of the material that we're going to talk about that's a little bit tougher. So that's up there. And then you have that Connect and Excel assignment, which you're also due by the end of the day on Friday. Okay. So start working on that if you haven't. I've already had some people reach out with questions. I've got a couple of Zoom meetings today set up. So I want to make sure we can get as much work on that early in the week as possible, so we're not kind of scrambling on Friday to send me questions via email, okay? Other than that, are there any questions for me before we kind of get started or jumping into things here? Okay, let's jump into it. So kind of a reminder of what we talked about last class, because we'll be using these contingency tables a lot today, is we said we have these contingency tables and these total columns, right, tell us the probability of the column or row heading. So the probability of A, we go over the total column, 0.6. Probability of A complement, 0.4, right? We kind of went over why we can do this on Friday, a little demonstration. If you kind of forget, you can go back and watch the end of last class. But we can add across the rows to reproduce these totals. So let's say I didn't have the total columns here. 0.4 plus 0.2 would give me that probability of 0.6. 0.1 plus 0.4 gives me the probability of 0.4. We can also add down the columns, same kind of idea. The probability of B is 0.5. The probability of B complement is 0.5. How could I reproduce those? Adding down the columns, right? 0.4 plus 0.1 is 0.5, and 0.2 plus 0.3 is 0.5. Okay. We also said these top 4 left cells all represent intersections, right, of whatever their row and column heading are. So if I wanted the probability of A and B, the probability of A and B is 0.4, right? Or that intersection, that upside down U, we kind of read that as A and B. And then the probability of A complement and B complement would be that 0.3, right? So the intersection of the complements here, we could find in that cell, right? So it's kind of where we left off on Friday. I think I then showed you maybe briefly this and said, we'll wait until next class. So what if I wanted to find the union of 2 events, right? So this set symbol, it looks like a U. What's the probability of A union B? Or the way that we typically say this in English, A or B, okay? So the probability of being an A or B, right now I'll show you kind of a non-technical way to remember it, and then I'll kind of break down why it works, right? So the non-technical way to remember how to find the union of 2 events is go to their intersection. So instead of A union B, go to A intersection B, this 0.4 right here, and then make like an L, right? If you add these up, this will give you the union of the 2 events. So let's say I wanted the union of A complement and B complement. I would go to the intersection, make an L, and then add these 3 up. Okay? Now, that's not a great way to know something. So we're going to break down why that works, but in a pinch, that works, okay? So we'll talk about a couple laws, and then we'll kind of return to that, and I'll show you why that works to find the union. Okay? So one thing that we want to get out of the way here right away is it doesn't matter if we're talking about the union or the intersection events. It doesn't matter which way it's written. So if I say, what's the probability that someone is over the age of 65 or they're over 6 feet tall? That's the same thing as saying, what's the probability someone's over 6 feet tall or they're over 65? Right? It doesn't matter which way I say that, right? So the union of 2 events doesn't matter the order in which I say that union. Same thing for the intersection, right? If I want the probability that someone's over 65 and they're over 6 feet tall, it's the same as saying, what's the probability they're over 6 feet tall and they're over 65, okay? So the ordering doesn't matter. And we'll use that a little bit throughout today's discussion. Not a ton. Next class, we'll use it more than today. So it doesn't matter which way we write. That's kind of our first probability law. Okay? Whoops. And then kind of we can think about another thing we talked about last class in identifying is if I have event B, which is this entire circle here, and I have event A, where those two circles overlap, we think about that's the intersection. Those are the experimental outcomes that are in event A, but they're also in event B, right? So that intersection is what's in between. So, you know, the meme of when you say it's fine and when it's actually fine, right? The intersection of those two events is very, very small, okay? Now, another thing that I believe I touched on Friday is this idea that, all right, this entire experimental outcome space represents the value of 1, right? We said if we took the probability of every possible outcome and we added them all up, well, we've looked at every possible outcome. That should be 100%, or probability, right, is percent in decimal form, so a probability of 1. So this rectangle's area is an area of 1. Think about it that way. All the experimental outcomes in event A are in this white circle, and then everything that's not in event A complement, is this kind of shaded blue area, right? So if I add that white area to that blue area, well, that is every possible outcome. So I know those two things have to add up to 1. Right? So the probability of A plus the probability of its complement have to add up to 1. If I do a little bit of algebra there, I can rearrange that equation. So think about it as, I'll type this in here. Right, so what I originally said was that if I took the probability of A and I added that to that, the probability of A complement, those two things should add up to 1. I'm just rearranging that equation a little bit to say that if I want to find the probability of the complement, it's just 1 minus the probability of that event A. So this kind of helps us. You know, if I said, let's think about as event A being the probability somebody has blue eyes. And let's say, I don't know, I think this is wrong, but the probability, let's say it's 0.1, okay? If I know the probability of A, that someone has blue eyes, is 0.1, what's the probability that they don't have blue eyes? Intuitively, it's 0.9, but what did you really do there? You said it's really 1 minus the probability that they do have blue eyes, right? So 1 minus 0.1 would give you that 0.9, okay? Any questions on that? It shouldn't be too bad. All right, so like I said, a lot of this is kind of review, throwing in a couple of things. So the next thing we're going to talk about is if I want to find the union of two events, there's 2 different ways we can think about this. So I'll show you what I think is the easiest way first, and then I'll show you the second one, okay? And by all means, you may disagree with me, but I'll show you what I think is the easiest way. So the easiest way to think about the union of 2 events, A or B, well, if I took this circle A and I added to that circle B, right? What I've done is I've double counted whatever is in both of them, right? So if I want the union of the two, so I could be in A or in B, or I could be in both, right? I just in one or the other. If I add the probability of A to the probability of B, well, I've double counted whatever outcomes are in both. So if I've double counted it, how can I only count it once? Well, I'll subtract it out, right? That way, instead of counting it twice, I've now only counted it once, okay? So if I want the union of 2 events, I can simply add up the probabilities of those events and subtract out what I double counted, which is just what's in both. What's the intersection? What's in A and in B? Okay? We talked about last class, we can think about the union, we think about as or, and the intersection, we kind of say in English as and. Okay? So I think that's not too bad. Right? We're just subtracting out what we double counted. And I could, dive in this a little bit deeper. Let's say I want to do it this way. Let's say I took circle A and then I subtracted out the intersection. Well, now I just have this half crescent moon, right? And then so that was the probability of A, subtract out the intersection. I then want to take the probability of B but subtract out the intersection. So now I've got this crescent moon over here. And then so now I have this area, all that I left to have to count that's in the union is what's in both. So I then add in the intersection. Kind of a longer way of getting at the same thing, but you'll notice here things cancel out, and I'm left with the union of two events is just add up the probability of each event and subtract out that intersection. Okay? There's a different way of thinking about it. I would never suggest like actually doing this every single time you're trying to find a union, but that's another way of thinking about the union. Okay? We can kind of break this down into three different components. Okay? But once I know that this equation will work, notice, if we go back to the original way I told you to find the union, which was make this L, which is very technically not a great way to remember this. The probability of A and B was 0.4, and then I made the L. So if I add these up, 0.4 plus 0.2 plus 0.1 is what? 0.7? So my union is 0.7. I think I must have said something in Siri's going off like she's waiting for me to tell her to look something up. Okay, sorry about that. So the union here I had was 0.7, right? If I use this method, right, where I add up the probabilities and subtract out what I double counted, well, how could I use the contingency table to do that? Well, what's the probability of A? 0.6 plus the probability of B, which is 0.5, right? So I can plug in 0.6 and 0.5 here. And then I subtract out the intersection, or what was double counted. Well, what's the intersection? Probability of A and B is 0.4, right? So probability of A, 0.6, probability of B, 0.5. The intersection is 0.4. I go ahead and do that math, I get the same thing I did before, which is 0.7. Right? Now, I think this way is the best way to remember it. For one, it's not this whole, like sometimes your L's are looking like this. The other times they would look like they're not going to completely look like L's. I called them L's, but they're really not. This way, you're always, it's very easy to grab the totals and to grab the intersection and then plug them in. And also, this is probably just a better way to think about what the intersection is, right? The reason why you're to think about what the union is. The reason why you're subtracting the intersection is because you're double counting it, okay? Excuse me. Any questions on this before we keep moving? All right, so I'm going to show you another way to think about the union. And this is fine if you want to think about this way and solve for it this way, but this is generally, I think, not, I don't think it like syncs up with our minds as much. It's a little bit more complicated, but I'll try to give you some intuition with a visualize behind why it works. So let's say, there we go. Let's say I've got this entire experimental outcome space, right? And let's say circle A is right here. And let's say circle B is right here. Okay? Now I'm going to break this down into three components. Okay? So the easiest, I think, that we've already talked about is what's in both of these events, right? Well, that's just the probability of A and B, right? I'm in both of those circles at the same time. So here, and I'm going to try to draw these so that if you don't have colors, it's okay. But some of the stuff we'll do in this class, it's like a lot of econ classes, colors sometimes help, right? But if you're taking notes, kind of try to draw the way I'm doing this. So let's think about where would B complement be? Well, B complement is everything that's not in circle B, right? So I could literally just take lines and kind of shade in the area that's outside of that circle B, okay? So this red kind of represents B complement. So if I want to think about what is this crescent moon kind of on this side? Well, that's everything that's in circle A and not in circle B, right? It's kind of where circle A overlaps with this shaded red area, which represents not being in B or B complement. So this kind of crescent moon over here is the probability that I'm in circle A and I'm not in circle B or in B complement, okay? Now let's think about where A complement would be. Well, that's everything that's not in circle A. So I'm going to draw vertical lines here that aren't in circle A. Okay, so you can think about as this blue shaded area would be A complement, right? So now I've got this crescent moon over here. I have kind of what's in both of them. And then I have this crescent moon that I still need to figure out what that is, right? Once I have this crescent moon, and kind of the intersection, I could just add those three parts up and I'd have the entire space that represented the union, right? I mean, either in circle A or B. So this crescent moon is everything that's in circle B, but not, right? This blue area is not in circle C or A complement. Sorry, not in circle A or A complement, right? So this crescent moon over here represents I'm in circle B and I'm not in circle A or A complement. So if I'm thinking about, well, what does the area within either one of those circles represent? Well, that's what we were saying was the probability of A or B, right? I could be in anywhere in this space. Well, I could break that down into these three components. So if I add these three together, I should get the union. I'm going to try to do something here. It's a little, it worked last class, so hopefully I can reproduce it. What did I do? I went back. I'll change this. Here, I'll stop this share real quick. I'll get that back up on the screen in just a second. This is a little clunky, but I think it's worth taking a 15 seconds for, okay? So you guys can still see that. So I actually want to go now to share my screen. Oh, please work. Otherwise, I'm going to have to remember what I did. All right, the moment of truth. All right, I got it right on the first try. Awesome. So let's go back to when I told you could make that L and just add up those components, right? So why did that work? Remember, we just broke it down, the union down to three components here. Where's the probability of A and B complement? Probability of A and B complement, plus the probability of A and B, plus the probability of A and B, plus the probability of B and A complement. So that's why like making that L works, because it represents kind of each of those crescent moons and then whatever the intersection is. So, you know, I think this way is a little bit harder. I think it's probably easier to just take the probability of the two events, the totals there, and subtract out what you double counted the intersection. But this is another way of finding the same thing. And sure enough, right, when we add these three values up, we got that same answer of 0.7 for the union, okay? Any questions on that before we keep moving? Anyone on Zoom? Look at the chat here. We're good? Okay. All right. And I'll try to do some more of this now that if I can remember the steps, so we can kind of have this whatever I had in the dot cam, so I don't have to just kind of like reference the slides. We can kind of see them at the same time. But for now, so we're not thinking of like the video stalled if we're on Zoom and also doing other things. I'll put my face back up, right? So where were we? We went through this. We went through this. The next thing we'll talk about is just introducing a definition, an idea that will make some things easier. It'll also just pop up probably throughout the rest of the course, really. I use this in my everyday language, and it's becoming a problem. But we say that two events are mutually exclusive if they can't happen at the same time. So I think the one I said last class, so let's say what's the probability if I select a person at random that they're in between the ages of 10 and 20 and they're in between the ages of 50 and 60? That's impossible. There's no age that I could be in both those categories, right? Or both of those events. So that's the idea of being mutually exclusive. And basically what I'm saying is if they can't happen at the same time, there's no overlap. There's no intersection. So what would the probability be if there is no intersection of those two events? it's 0, as low as it can get. It just can't happen. The probability is 0. Right? Now, just kind of mentioning here, this is really nice because if I'm trying to find unions, I'm not double counting anything, right? We'll come back to here in a second, but if we think about the visual, if I take the probability of A and I add that to the probability of B, I haven't double counted anything, right? There's no intersection there. Okay? Also, if the definition is that they can't happen at the same time and the probability of the intersection then is 0, what do I have to see in that contingency table up here? Well, I'd have to see a 0, right? Because this represents the intersection of A and B. So if I'm given a contingency table, or on Wednesday, like we'll see, we're going to actually create our own. It's pretty easy to tell if things are mutually exclusive because if I see a 0 in that contingency table, I know they're mutually exclusive. If I don't see a 0, I know they're not mutually exclusive. They can happen at the same time. Okay? Any questions? This one's not, I don't think this is too bad of a definition, especially with the visual, kind of thinking about the contingency table here. I always like this example, if I can get to it, right? In the 90s, phone and internet access were mutually exclusive. So you guys are getting a little bit younger, but some of you will at least remember what I'm talking about. So like, it used to be you have to have 2 phone lines in order to use the internet and the phone. So I got yelled at a lot in like middle high school for being on the internet and basically everyone calling is getting a busy signal, right? Because you can't actually use both of them at the same time, okay? And you can think of tons of other examples. Like I said, this will pop up throughout some of the other topics we'll talk about in the semester. So this idea of mutually exclusive will pop up again. Okay, so I want to make sure I mention that. But now we're going to kind of return to this idea of how we can rewrite the union. Okay? So let's say I have something like this, and we'll come back to it here in a second. The entire experimental outcome space is 1, right? That represents the probability of every single possible outcome. If I broke this down where I'm thinking about this white area here, well, that just represents the union of A and B. Right? If for now, I'm going to tell you that this is what it is, I'll show you why it is in a second, but everything that's not in this union of A and B, or this blue area, I can actually write that as the probability of the intersection of the complements of these 2 events. So the intersection of A and B complement. So if I took this blue area and I added to it the white area, that has to add up. It fills up the entire space. It adds up to 1. So this, right, if I add the probability of the union, that's the white area, to the blue area, or the intersection of the complements, these 2 things have to add up to 1. Okay? From there, I know that I can rewrite the probability of the union as the probability of the 2 events minus their intersection. So if I just substitute in what I already know for how I can rewrite that union, I know that this equation, these 4 components, have to also add up to 1. Okay? So anytime I don't know one of these, as long as I know 3 of them, I have 1 equation, 1 unknown, I can use algebra to solve for it. All right? So we'll work through a couple examples like this. But before we do that, I'll try to give you a little bit of insight as to why this shaded blue area is the intersection of these 2 events. So we'll go back to our dot cam here. So let's draw an experimental outcome space. All right, let me see. Let me try to get this straight here. So let's say I had something like this. And I've got event A, and I've got event B, right? So I kind of think about the area within those circles is the union of the 2. Well, remember, before we did a very similar thing. Let's say I wanted to look at B complement. So I draw my vertical lines, everything that's not in B, right? I then want to take A complement, everything that's not in A. So I take circle A and start drawing these red or these horizontal lines if we don't have colors here, right? So it might be a little bit hard to see, but notice the only areas in which the red and the blue shaded area, the lines intersect, is everything outside of the union. So if it's where A complement and B, sorry, I should write this here. The red area here, the horizontal lines was A complement. So everywhere where the blue and the red shaded areas intersect, well, that means that I'm in both A complement and B complement, right? So that's why everything outside the union I said I could think about as the intersection of those two events complements. Right? That's why that holds, okay? We okay with this? So from here, I'm going to go through two examples where it's once we know that equation holds, it's really just going to be a matter of doing a little bit of algebra. So I'm going to have to hit this here. See if I can get it on the first try. I might have hit it a little bit too late. It'd be really nice if it just automatically did this, but nope. All right, I hit it a little bit too late. Now we should get going. There we go. So let's say I give you 3 of these pieces. Let's say I had a problem like this, right? I tell you the probability of A, right? And when I'm telling you the probability of A, it's this entire circle, right? The whole circle represented A. I don't know the probability of B, but I know the probability of their intersections, right? The kind of area that's in both of those. I'm also giving you the probability of the intersection of the complements, or this light blue or kind of grayish area out here. Well, I know that those 4 components would fill up this entire experimental outcome space. They have to, I can use those 4 to figure out that the union plus the intersection of the complements add up to 1, plug in for the union, the equation I know that holds, and solve for this missing piece. So how do I do that, right? Well, here's that equation. We know that if I take the probability of the 2 events and subtract what I double counted, which is the intersection, and then add the intersection of the complements, this kind of light blue gray shaded area, they have to add up to 1. So what I could do here is just start plugging in my values. The probability of A is 0.5, the probability of intersections is 0.1, the intersection of the complements is 0.3, and then it's just, once I have those plugged in, a little bit of algebra to solve for what that missing component probability of B is, right? You could actually, if you wanted to, once you plug the values in, just rewrite probability of B as X, and it becomes like a algebra equation, basically. But that's all we're doing, right? So plug in your values into that equation that you know has to hold, and then rearrange to solve for the one part that you don't know. Okay? Now, I'm not going to go, line by line, step by step through the algebra. If you're having problems like plugging this in, how did I get from here to here? Feel free to reach out. I'm kind of expecting that, it's kind of some prerequisites. You should kind of understand the algebra or be able to reproduce the algebra here. But if you are having issues or difficulties, like reach out, let me know, and I can kind of walk through. I'm just not going to take class time to do it, okay? But during office hours or even a time we schedule to meet, we can kind of walk through that a little bit more line by line, okay? So if we do that, we end up with we end up with 0.3. Okay? Any questions on what I did here? I know if you're just looking at the slide, it may be a little bit less clear. I tried to kind of give you some verbal, like, we're just plugging in our values and then doing our algebra to rearrange for the one thing we don't know, okay? Now, the one place where you can kind of get tripped up a little bit is maybe a little bit more apparent here, which is, let's say I ask you for what's the intersection of these two. So maybe the intersection of the 2 events is what I don't know. Okay? So I know that the entire circle B, the probability of B is 0.3. The entire circle of A, the probability of A is 0.3. This gray area, or the intersection of the complements, is 0.5. And I ask you to find me what the intersection is. Okay? The reason why this can become a little bit more tricky is if I use that equation, I have to remember there's a negative sign in front of that intersection. So when I'm rearranging, I have to remember that negative sign is there, right? So what I'll show you here is if instead of plugging the numbers in first and then rearranging, if I rearrange this equation to solve for the one thing I don't know, I'd have to remember that, look, I'm adding this to the other side, and then I would subtract 1 from both sides. So it gets, a little bit tricky. Most of the time, if you forget that negative sign, it's okay because you'll end up with an answer that's negative, and you can't have a negative probability. So you know that you made an algebra mistake somewhere. You forgot a negative sign, right? Because we're still looking for a probability. It has to be between 0 and 1. Okay. So we rearranged the equation first this time. I mean, we can do it either way. I'm just showing you two ways. So if I rearrange this equation to solve for the thing that I don't know, now I plug my values in. So the probability of A is 0.3, B is 0.3, intersections of the complement is 0.5, and then it's just a little bit, entering this into our calculator, and we get that intersection should have been 0.1. Okay. So I think once we have that equation and understand kind of why it holds, this is really just kind of an exercise to a degree in algebra. Right? We're solving for the piece of the equation that we don't know. Okay? And more often than not, this will probably be the intersection of the two events, but it could be one of the other three components. Okay. Any questions on this before we keep moving?
Well, I have a question.
Yep.
So if I know that it has to equal 0.1 and I add up everything that's given and it's like or it's like 1.3, then can't I like automatically know that like what's missing is 0.3? Like if it's the intersection?
Yeah, you're for sure, right? You could do it that way. If you are looking for the intersection, right, and you add them up, they're going to be over the value of 1. So what you're saying is if I add these up and I don't include the intersection and I get 1.3, I automatically know the intersection has to be 0.3, right? I automatically know that in order for them to add up to 1, I'd have to be subtracting out however far above 1 I am. That's another way you can do that. So that's a fine way of thinking about it. Yeah, that's fine. You're really just leaving off this component and knowing that you have to subtract it out. But yeah, that's perfectly fine.
Thank you.
The other thing that people get tripped up on is the way that this is displayed here. Don't think that like the probability of B here, don't think about it. Sometimes people can make the mistake of visually thinking about it as though it's this half moon. I really could have had it like here, right? It represents this entire circle. So that's the other common mistake I see people make that want to do this in their head, because you can very easily do this in your head without ever looking at the formula. But the problem most people are into if they do it in their head is like the visual. When you're thinking through this, I do the same thing. For some reason, you think about this probability of B as being like this crescent moon. And if you try to do it in your head, a lot of times people will kind of, I don't know, kind of get that wrong. It doesn't represent just this crescent moon. It represents the entire probability of B. Okay? Any questions on that? No? Yeah. Stretching. All right. Okay. So if we don't have any other questions up to this point, and I'll go back here and we'll kind of return to this. So any questions at this point? Okay. So I'm going to actually work in reverse. I decided that I like explaining things a different way first, and then we'll kind of come back to this slide. So one thing that I brought up on Friday, but we really didn't dive deep into it, so I wanted to save it for today, is this idea of conditional probabilities. Okay? So if I'm thinking about conditional probabilities, the way that we read this is the conditional probability of A. Okay? And the reason why we say it's sorry, I said that backwards because I was looking at the other one. This is the conditional probability of B. And the reason why we say that is because we're conditioning on something else. Whatever's on the right-hand side of this line, that's what we say we're conditioning on. So we're conditioning on A, but we're still looking for the probability of B. And the way that we usually read this is the probability of B given, this vertical line we kind of read as given, event A has occurred. Okay? So how could this conditional probability change things for us? So I'll try to give an example that I like. I don't know if everyone else likes it, but I think it makes sense. So, and this is using a generality, but if we look at the data, this is supported. So let's say event B, right? So we're thinking here, event B is whether or not, if I ask a person at random, they are in favor of supporting marijuana legalization. So I've looked at the data for Indiana. I think it's like one of the last polls they took was like around 60%. So the probability if I chose one person at random that they'd be in favor of supporting legalization of marijuana is about 0.6. right? 60%. But now let's say, well, what's the probability they'd be in support of legalization given, so you have another piece of information, given that you know that person is a registered Democrat? What do you think probably happens to the probability that they're supporting it? I see people pointing out, right? It's probably higher than 0.6, right? I don't know the exact date on that one because I didn't have it broken down in the poll, but based off all the things that we've seen, voting records, we know that it's likely higher, right? And then if I told you what's the probability they support it, given that they're a registered Republican, well, you know it's probably going to be a little bit lower, right? Having this additional piece of information allows you to get a better idea about what that probability is. And that just makes sense. If I have more information about the person, I'm going to be able to not just use the average of everybody, but the average of whatever their political group they belong to, right? So this idea of conditional probabilities, that's what we're doing. The other one I always give, but it doesn't work as well in the spring semesters. But let's imagine, right? This is just across any day in the year. What's the probability that if I'm walking into the building, I slip and fall? I haven't slipped and fallen yet, so pretty low, right? However, if it was a day like even today, but a day where it's really icy, it's really, really cold, it's kind of rain, snow mix, maybe like, was it Friday it was like that, right? The probability that I slip and fall is a lot higher, right? One of the things I'll never forget about when I was an undergrad is how many people I saw slip and fall off the bus in the winter, right? And so knowing the weather conditions greatly influence the probability of that event that I was thinking about, right? So that's the idea of conditional probabilities. But why does this equation hold, right? Why can I find that conditional probability as the intersection of those two events divided by what I'm conditioning on? So I'll try to give a visual. We'll get a couple of these. We'll return to this idea even on Wednesday, but I think this one will give a pretty good idea of why we can write it this way. Okay, well, there we go. So I've been drawing up to this point circles to represent the events. They don't have to be circles. I could draw them, it could be any shape. So I'm going to use rectangles here because I think it just helps fall in line with the numbers a little bit better. So let's say this entire area here, let's say is event A. And I tried to draw this in such a way that it looks like it's exactly half of the entire experimental outcome space, right? So let's say like 50% of the outcomes are in event A, okay? Let's say I then take this like little rectangle or square over here, and I'm going to call this event B, okay? So what is the probability of A intersected with B? Well, I tried to draw this to like exactly split it in half. So really this rectangle of B, which is entirely intersected with A, the way I do, this is a very extreme example, right? I'm trying to draw proportionally. Let's say it's 0.25, right? Like you can think about like you have two squares here and then like a large half up there. So if I ask you for just what the conditional probability of B is, right? Well, this is a unique scenario in which all of event B is within A, right? So if I'm thinking about event B, it's really the same as the event B intersected with A, because I'm drawing this as an extreme example. So we call this the unconditional probability of B. Oh, sorry. Try to get this all in one line here. Okay. What if I want the conditional, so we'll call this is the conditional probability of B. Because we're still looking for the probability of B, but we've now conditioned on something else. Okay? Well, if the area of B intersected with A is 0.25, and now that I know A has occurred, essentially what I'm saying is the entire experimental outcome space is no longer 1 because I'm telling you that A has occurred. So now the only outcome space left is 0.5, right? Or whatever the probability of A was. So here, we can think about the entire experimental outcome space left is no longer like out of 1, it's only out of whatever the probability of A is. Right? And what's the probability that now that we know we're somewhere in A, what's the probability that we are in B? Well, out of this entire space of 0.5, 0.25 of it would be that I end up in event B, which is really wherever probability in A and B intersect. Okay? Now, I drew this one as an extreme example so that all of B was within event A. Okay? So here it was kind of odd because the probability of B and the probability of the intersections were the same thing. Right? But what if that wasn't the case? Would this idea still hold? Well, let's go back here. Let's say now the probability of B, let's say I make it 0.3. But I just extend it up here, right? So now the intersection of A and B is still 0.25. And now when I condition on A, it goes back to the exact same thing, right? Because saying that I'm conditioning on A eliminates all of the possible outcomes that weren't in A, right? So that's why we don't use the probability of B here in the numerator, where we just use the probability of the intersection of A and B, right? Any questions on that? Well, it's kind of a lot. Just trying to give you an intuition behind why that equation holds, okay? Because it's essentially like once we condition on this other event, we're like limiting the space that we're looking at, okay? And I could actually come up with like a really crazy one. Like, let's say event B was actually all the way out here, right? Well, then it doesn't matter, right? Because once I condition on A, I'm still back to the same thing, right? It just matters where the intersection of those two events are. Okay? Any questions on that before I kind of keep moving here? We're okay with that? All right. Wait. We got that time. So there we go. So let's say, so that's what we just went through and found here, right? That the conditional probability of this event B is the intersection of these two divided by whatever I'm conditioning on. So here, when I'm conditioning on B, divide by what I'm conditioning on. Right? And it doesn't matter which way I write the intersection, right? So even if I wrote the intersection, the probability of B intersection with A here, remember what we said earlier, A and B is the same as B and A. It doesn't matter which way I say that. Okay? So if I work backwards from here, because I think the other way is a little less intuitive, but let's say I just rearrange these equations. So like we're going back a slide now and we're rearranging this. Multiply both sides by the probability of A. And the equation I would have is that the intersection of two events is the same as the conditional probability times whatever I'm conditioning on. And this is kind of nice because it doesn't matter which way I write this intersection, right? But if I write it this way, I could also find the intersection using a different conditional probability and then multiplying by whatever I condition on there. So there's really two ways of finding this intersection. Because it doesn't matter what order I write the intersection, that's the exact same thing. Right? The ordering didn't matter there. Okay? Any questions on this? Okay with that? All right. I don't know. I like the visual I did better than this one, so we can kind of ignore this. But the idea would be, you know, if I'm looking for the probability that I see A and B, what I'm really looking for is this place where they overlapped. So the likelihood that I'm kind of within, you know, I'm in there is, well, first I have to know that A has occurred. Well, if A is not very likely to occur, then it's very unlikely for me to see the intersection of A with anything else, right? And so that's why you're kind of thinking about is whatever I'm conditioning on, my space gets kind of limited down to just that area. And that's kind of what I showed over here. I liked what I did in the dot cam a little bit better than the slides. So we can kind of ignore this drawing. I think the other one makes a little more sense. So all we did was rearrange that equation there. And now we've got kind of, here's our summary. We've got that complement rule. We've got our addition rule for finding the union, and we can rearrange that a little bit, right? We said to find different components. And I can also have this multiplication rule where I can solve for the intersection, or I could rearrange it and I could solve for conditional probabilities. Okay. So once we have this multiplication rule, let's go back to our contingency table, right? If I want a conditional probability, I can't directly get that from my contingency table. Like it's not one of the cells up here, right? But can I change the font here easily? No, there's some option. Here we go. Let's make it real big. So if I want the probability of R1 given C2, I know that I can rewrite that as the probability of the intersection of the two, right? And then divide by whatever I'm conditioning on. That was I'll go back in a second. That was the equation we had. So what I'm really looking for here is I'm gonna have to write it in words. Well, can I do an upside down U? I know there's symbols somewhere up here. Forget it. We'll just do the intersection of the two. So intersection with C2. And then we divide by the probability of whatever we're conditioning on, which is C2 here, right? So where is the probability of R1 and C2? Probability of R1 and C2 is 0.2. The probability of C2, go down to the total, is 0.5. Right? So hopefully, oops. Oh, so with that, I was just kind of writing out as I was saying it because I have it on the slide here, right? So the intersection of R1 C2 divided by C2, so 0.2 divided by 0.5 would give us that 0.4. Right? So even though we can't directly get it from that table, we can use, right? We can always find intersections and we can always find the probability of events themselves from this table. And that's a little bit of work. We can always find those conditional probabilities from that contingency table. Right? It's just not quite as easy as finding just the intersection. Okay. Any questions on that one before we kind of get out of here? Okay with this? So what we're going to do next class is I'll kind of use this idea of conditional probability. So I'll probably review it a little bit. We'll talk about independence, some interesting things that I think are kind of fun applications of that. But then we're going to hop into Excel, right? So a lot of next class, we'll primarily be looking at an example in Excel. There's already, it's called union data. It's a file in the in-class data folder on Canvas, and we'll be kind of working with that data on Wednesday, okay? All right, if there's no more questions, I will see you guys on Wednesday, okay? And I'll leave Zoom open here for a second or two.